All right, let's look at our next example, which says a real estate investor buys a parcel of land for $150,000. He estimates that the probability he can sell it for $200,000 to be 40% or 0.4. He can sell it for $160,000. That probability will be 0.45. Or he can sell it for $125,000, which the probability would be 0.15. So what is the expected profit for this purchase? First, of course, we want to make a probability distribution to be able to find expected value. So let's go over here. We want to put the profit and its corresponding probability. All right, let's have you guys pause the video and fill out the probability distribution table, and then we will look at it together. All right, the profit will really be what he thinks he can sell it for, subtracting what he bought it for. So the first profit is $50,000 if he were to sell it for $200,000, and that probability is 0.40. The second profit would be $10,000 similarly, and he'd sell it, and the probability would be 0.45. And finally, if he sold it at a loss for $125,000, his profit would be negative $25,000. And that probability is 15%. So let's go ahead and have you guys write out what the expected value would look like if you were multiplying those together and adding. Pause the video and we'll meet you on the other side. To calculate expected value, we take the profit times its probability in each case and even the loss, so we represent that with a minus. Go ahead and find out what that value is. All right, calculating this, you should have come up with $20,750. So we'd interpret it by saying if you purchase this property and your estimated probabilities are correct, you can expect your profit to be $20,750 when you sell. Let's look at our next example. Here it says the cost of a $50,000 life insurance policy is $150 per year for a person who's 21 years old. Assume the probability that this person will die at age 21 is 0.001. What is the company's expected profit if the company sells 10,000 policies to 21-year-olds? So again, we need to write out the probability distribution before we find the expected value. Let's have you guys do that. Pause the video and we'll check it together. So here, if the 21-year-old lives and the 21-year-old gave the insurance company $150,000, the company's profit would be $150,000. Now, to find the probability, we know that on average, the probability that a person that is 21 will die is 0.001. So if we subtract that from 100%, or 1, we get the probability that they will live to be 0.999. Now, if the 21-year-old dies, they got his $150, but they have to pay him $50,000. So in actuality, they're really paying him $49,850 because that's the difference between those two. Let's go ahead and calculate that expected value. So calculating this, we should get $100 per 21-year-old's policy. So we expect the insurance company's profit to be $100 for each 21-year-old. So this question asked, what would the profit be if the company sells 10,000 policies? So we say, if the company sells 10,000 policies to 21-year-olds, they can expect to make 10,000 times 100 or $1 million. All right. So those are a couple of examples using expected value. Let's go ahead and look at a definition that we'll have here that says that a game with an expected value of 0 is called a fair game. So this isn't left up to subjective interpretation. If I ask you if a game is fair, you're going to use the criteria that its expected value must be equal to 0 to decide that it's a fair game. All right, let's look at another example. This one is a little more complicated. It says a carnival game consists of drawing 2 balls without replacement from a bag containing 5 red and 8 white balls. If both balls are red, you win $6. If both balls are white, you lose $1.50. Otherwise, you lose $1. Is this a fair game? What would you expect to happen if you played the game many times? Now, one thing we have to take into consideration here is that they are not replacing the balls from the bag after they draw them. So figuring the probability is going to be part of the challenge in this problem. Let's go ahead and see if you can make that probability distribution table, and then we'll calculate the expected value. So this is how we calculate these probabilities. If we drew 1 red and took it out, then there would only be 4 red left, and there would only be 12 total. So for the first red, it would be 5 out of 13, because there were 5 red out of a total of 13. But for the second red, drawing the second red without replacement would be 4 out of 12. Similarly, if we were drawing 2 white, since there are 8 white, to draw the first white ball out of the bag, the probability would be 8 out of 13. But once it was gone, the probability would be 7 out of 12 to draw the second white ball. So multiplying these probabilities is how we got the probabilities for these. For 2 red, it's 20 out of 156. For 2 white, it's 56 out of 156. Now, to draw 1 red and 1 white, we could either draw the red first and the white second, or the white first and the red second. So instead of calculating those 2 probabilities and adding them together, since this is the complement of the previous 2, we can just take 1 minus the sum of these 2 probabilities to find all the other possibilities. So the probability of 1 red and 1 white would wind up being 80 out of 156. Whew. Now we need to calculate the expected value by multiplying the dollar amounts times their probabilities. So taking each of these dollar amount times their respective probabilities yields us a negative 0.28. Now you might be more inclined to want to use fractions, not fractions, but decimals when you're calculating your probabilities. And that's fine. Just don't round the decimals off until you get to the end, because the more rounding you do in each step, the more likely it is that your final answer will be inaccurate. So if you can bear keeping it in fraction form, you're more likely to get a correct answer at the end. But as long as you don't round your decimals to the end, you can do it that way too. So what we wind up here with is a negative 0.28. So to interpret that, we would say for this game, you can expect to lose 28 cents on average each time you play. Of course, you're losing because your expected value is negative. Let's go on to our next example. Example 5 is less of an example and more of an explanation of the law of large numbers. So let's say you're tossing a fair coin 7 times and recording which side lands up. For example, HHTHTTT would represent getting a head on the first and second and fourth tosses and a tail on the other tosses. Is a streak of all heads less likely than any other possible outcomes? Well, as we will see in section 3.5, there are 128 possible ways to toss a coin 7 times. So some of those options could look like these here. But because coin tossing is independent, then each time you have the same probability of getting a heads or a tails. That means that the probability of getting HHT is 128, 1 over 128. And so is this combination, which also means that the probability of all heads is the same probability, 1 over 128. So getting a streak of all heads has the exact same probability as any other one possible outcome. Now, the law of large numbers means that with the larger number of trials of an experiment, the observed empirical probability of an event will approach the calculated theoretical probability of an event. So what that means is, so say I toss a coin twice and I get 2 heads. I get a head on the first toss And then since the second toss is going to be independent, I might just get ahead on the second toss also. Now that's not that rare. However, if I tossed a coin 1,000 times and every time it turned up heads, that would be less likely. So what this is saying is the more times I would toss a coin, the more times that I should wind up with half of the tosses coming up heads and half the tosses coming up tails, because that's the law of large numbers. All right, in our next video, we will look at different counting methods, including permutations and combinations. Thanks for watching.